Okay, so these are a series of images and tables from chapter 18. The table 18.1 actually showed this information before, that the molar heat capacity for monatomic gases are 12.47, like we said that they should be just now, and that the diatomic molecules have higher molar heat capacities. Um, and the explanation for the difference is it's actually due to quantization of energy, and it's one of the sort of achievements of early 1900s quantum mechanics, that it helps to explain the differences in these molar heat capacities. This is one of the reasons that it was as persuasive as it was to the scientific community, is that it helped explain these discrepancies that otherwise we would not really have a way to explain. The crux of the explanation is that every freedom that the molecule has contributes an additional half kT worth of energy. The 3 halves in our molar heat capacity at constant volume for a monatomic gas, the 3/2, that 3, instead of 1/2, the fact that it's 3 R/2s comes from the fact that a monatomic molecule has 3 axes along which it can move. Those 3 degrees of freedom get us the numerator 3. A diatomic molecule can, on it, as itself, translate along all 3 axes like a monatomic molecule can. So it has at least 3 degrees of freedom. There's one more thing it can do, though. And that's rotate. A diatomic molecule can rotate around the pictured y-axis or the pictured z-axis. And as we are here standing looking at it, we can tell the difference. We can say, yes, it is rotating because M1 is moving towards me and then moving away from me. And I can see that happen, and that's rotation around the y-axis. Or I can see rotation around the z-axis as M2 rotates counterclockwise up from X to Y. I can see those things happen. Those axes are independent. They could be happening simultaneously. One could happen, the other could happen, doesn't matter. So that's an additional 2 degrees of freedom. Rotation around the x-axis, we don't really count. And that's because if there weren't writing on the marker, could you tell that it was spinning this way? The answer is no. If it were spinning towards you, sure, you could see the cap coming towards you. Or if it were spinning this way, yeah, you could see the cap moving. But if we're rotating around the third axis, that's not, maybe that's happening, maybe it's not, I don't know, that's not really free. There is a third thing that a diatomic molecule can do, but for gases, they only really do this third thing once the temperatures are high, higher than in a normal lab, and that's vibrate. There's one axis along which the molecule can vibrate. The bond between those two atoms is like a spring, and we've talked about the potential energy of two atoms in a molecule, that there is an equilibrium separation, and that we could, for small oscillations, talk about a simple harmonic motion between them. So that's the third thing. But again, it only happens at relatively high temperatures. We're talking thousands of Kelvin. We can, though, at normal room temperatures, above 50 Kelvin, which is very cold, but somewhere here in the 270, 300 Kelvin range, yeah, the 5 R over 2. Now 5, why 5? Because 3 axes of translation and 2 recognizable rotations. So we can get 5 degrees of freedom, and the molar heat capacity at constant volume for a diatomic molecule is 5 halves R, because we've got these 5 degrees of freedom. If we asked for the molar heat capacity at constant pressure, exactly the same algebra that we did would add another R. So we would go from 5 halves to 7 halves, and the ratio between them would be 7 over 5. 1 2/5, 1.4, like we saw in the table that I'll go back to in a second. Polyatomic molecules have orientations. Now, sometimes the third axis of rotation is distinguishable. Things can vibrate oddly. It's harder to sort of pin down polyatomic molecules to one particular value. But I suppose if we did include all the possibilities, then let's see, we're talking about, well, it depends along how many axes we can vibrate. It's basically molecule by molecule we have to evaluate a polyatomic. But monatomic and diatomic are reliably well behaved. And that's good news, because the diatomic molecules are of particular interest to us. Hydrogen, oxygen, and nitrogen. All diatomic molecules, and all doing something very like this figure here. The last piece of the puzzle, back when we were talking about molar heat capacities, we looked at a table that included some solid materials. And let me see if I can find that table really quick. Nope. Okay. The specific heat capacity for lead, aluminum, and copper were all very, very different. And the molar mass for all three are very, very different. But the molar heat capacity for all three were very, very similar. And the explanation is that a solid material lives in a crystal lattice structure, kind of like this one. The molecules can move in 3 directions, and there are kinetic energies in 3 directions. There are also explicitly interatomic bonds that we have to consider when we're talking about a solid. If it's a gas, the molecules are going every which way. But if it's a solid, it's staying put. Right? These atoms live where they live because of the interactions that are holding them there. So the potential energy of each atom with its nearest neighbors, there are three. So there are three kinetic energies because we could be moving in any of three axes, and there are three potential energies on average per atom. So we've got a total of 6 energies that could change. So the numerator here gets to be 6 instead of 3, and 6 over 2 is 3r. And if you multiply 3r, that's 25, which is what we saw for the molar heat capacities for the solid materials. The rule of Dulong and Petit. And that's a figure that shows the agreement with the Dulong and Petit prediction. As temperature goes up, these different solids all have molar heat capacities that approach 3R as our equipartition of quantum energies theory would suggest. Okay, let me go back to chapter 19. This is the last piece of the puzzle to finish chapter 19 is these molar heat capacities, and the equipartition of energies helps explain the difference between the molar heat capacities of monatomic and diatomic gases. And we've explained with the first law of thermodynamics the difference between the heat capacities at constant volume and constant pressure. Gamma is of particular interest when discussing adiabatic processes. And as I'm sure you found when calculating the work done during an adiabatic expansion. Note that we need to care whether the gas is monatomic or diatomic during an adiabatic process because the values of gamma are different. And that is all we have to say about chapter 19. And on to chapter 20.